Hello class and welcome to BME295 review of quiz number 2. So let's begin at the top where we are asked to solve this circuit using mesh current analysis. And in particular what we are asked to do is find the current through R2, which is this resistor here, as well as the voltage across R2. So as with every circuit analysis technique, there's several steps that we want to follow. The first thing that we want to do is assign our current loops around this circuit here. So we can assign these arbitrarily, usually. However, in this case, we are sort of forced in a current direction due to this current source here. And because this current source has a direction pointing downwards up through the circuit, then we are forced to assign our current loop to be in this direction. Likewise, because of this sort of forcing function, and noting here that current will flow from a negative to a positive terminal, we are also of a voltage source, that is, we are also somewhat forced to write the current moving in this direction as well. So let's assign this mesh current as I1 and this current mesh as I2. Okay, so we have that done. So the next thing that we want to do with a mesh current analysis is to write our KVL equations. So since we have two meshes, that means we're going to have two sets of KVL equations. So as I always like to do when solving KVL, as mentioned in the KVL KCL video, is I like to start at the bottom and follow up through the minus sign to the plus sign of any voltage source here. So sort of going in the direction of this current, we also want to make sure that we're doing that since we've already assigned it. We're going to start down here, move up through the minus, through the plus, and because we hit the minus terminal first, that means that this value we're going to assign a minus value. Now likewise with resistors, because a current is entering a resistor and there's a voltage drop across this resistor, we know that the potential on this side of the resistor is going to be larger than that of the potential on this side of the resistor. And that's likewise going to hold for the rest of these resistors. Things are going to get a little bit stranger here, and we'll get to that when we get to that. But we then hit this resistor, which is the voltage across the 10k ohm resistor. Now notice what's happening here at this resistor. We have I1 that's going down this direction of the resistor. However, I2 is opposing it. This is interesting in that now there is a superposition of currents occurring, meaning that these two currents are going to subtract from each other. Now, from the perspective of this mesh, we have the current entering this way and leaving this way. So what that is going to mean is that whatever the voltage across the 7.5 k ohm resistor, well, we're going to have this be a superposition of these two currents. So to get to that superposition, we reach the third step, which is to use Ohm's law to convert this equation here into a equation with respect to the mesh currents. So let's do that. So we have minus 10. The voltage across the 10k ohm resistor is relatively straightforward, and that is just going to be I1 times 10 kilo ohms. Now here's where this superposition part gets a little bit interesting. So let's look at what's happening. Again, we have a current from this perspective entering here and leaving here, and I2 is coming up through, coming up below and up. So what's going to end up happening is that from this perspective, this is going to be the plus terminal. So we're going to have I1 minus I2. because there's going to be, the currents are opposing each other, so there's going to have to be a subtraction. If this voltage sign was, or sorry, this current sign was flipped upward and our mesh current was going around this direction, then the superposition would be one of addition. Okay, so let's go ahead and do as we do and multiply that by 7.5k ohms and set that equal to 0. So now we have an equation for our first loop. So let's do the same thing for the second loop. Again, we are going to start from the bottom here, moving in the direction of the mesh current. So the current's going to go up through here, which, remember, based on our convention that we did last time, we had this current moving in. So this is the plus side and this is the minus. Now remember, a key step here is whenever we assign a direction, we need to stick with that direction. If we were to flop them, the math would still work out, but the important part is being consistent once we've written an equation down. So this current is going to go up through the minus sign, meaning that the voltage drop is reversed. So we're going to have a minus V 7.5K. And then again, we're going to have a positive. There's going to be voltage drop across this resistor, meaning that we have a positive on this end and a minus on this end. So that's going to be a plus V 5K. Oh, I should also mention, as always, these are equal to 0 because of conservation of energy. So now let's write Ohm's law for this second equation here. Now notice what this minus sign does. These, so it's going to be the exact same voltage, the V across the 7.5k ohm resistor, R2 in this case. However, we are subtracting it. So this sign is going to flip, meaning that we're going to have I2 minus I1 times 7.5k ohms plus 5k times I2. Now again, we could keep the minus sign here and have the signs flopped. It'll amount to the exact same thing, but for me it's a little bit easier to see it if I go ahead and bring the negative sign in and distribute it such that the currents look like this. Again, that's a personal preference. There's certainly, you'll develop styles for how you like to solve these problems as you do more and more of them. Okay, so let's continue on. So notice what we have here. We have two equations and what it appears to be two unknowns. But we have something quite nice in this particular problem, in that we can look and directly know what I2 is because of this current source. So I2 by definition is going to be 2 milliamps. Now we could solve for I1, which is what we need in order to calculate the current and the voltage across this resistor. We can go ahead and solve it with either one of these equations. You can choose which one you want to solve for. So let's just go ahead and use this equation to solve for I1, maybe because it's a little bit more complicated, so we can maybe show a couple more tricks using this side that might not be evident on the right side. So let's go ahead and do this. Let's bring the 10 over to the other side such that we have 10k I1 plus 7.5k I1 minus 7.5k times 2 milliamps is equal to 10. So let's go ahead and do some of the algebra here to make this clearer and to get I1 by itself. So then we get 17.5k I1, again just by adding these two resistors here. Evaluating this and setting these equal to each other gets us, right, minus 15 is equal to 10. So let's continue to do our math here, 17.5 K I1 is equal to 25. Okay, and then solving for I1 then gets us 1.429 milliamps. All right, here's the powerful part. Now we have all of the information we need to solve for both IR2 and BR2. So let's go with IR2 here, which, remember, is just the superposition, in this case the subtractive superposition, of I1 and I2. So we will have IR2 is equal to I1 minus I2. And again, that's because we assigned the plus for this resistor on this side and the minus on this side. Again, if you were to have flopped those, the math will still work out as long as you're consistent with how you assign these variables. And you can do it as an exercise to prove that to yourself as well. So that means that we are going to have 1.429 milliamps minus 2 milliamps, which gets us a value of minus 0.571 milliamps or so. And there we go. Okay, so then the next thing is to calculate VR2, which we can get by Ohm's law, and that will have IR2 times 7.5 K, which then gets us minus 4.283 volts. And there we go. So we solved this using Mesh's method, and we're aided a bit by noticing that the current here, this current source sort of forces our direction, as does this voltage source. So as you're solving mesh current problems, keep that in mind. Keep in mind what the source is doing and how it's forcing currents one direction versus the other. All right, moving right along here, let's go ahead and look at question number 2, in which case we are going to solve for the current through R2 and R4 of this circuit, but this time using node method. So if you need a review on node method, I would suggest going to my tutorial video, in which I go through in detail the sort of psychology behind node method. But for now, let's get started with our step procedure. Again, the first thing that you want to do with a node method is assign a ground. And when we're assigning a ground, we usually want to find a spot on the circuit which most components are connected to, and also has, mostly where most components are connected to, and if possible, has a nice connection to our sources. In which case, that's going to be this lowest line right here. Go ahead and drop a ground symbol right here. Again, you can choose any spot to be ground. However, the point which has the most connections usually makes the math a heck of a lot easier. So that's the strategy that I would take. Next thing we want to do is find and assign our nodes. Now, these nodes right here are a bit trivial nodes because we know what they are just by inspection with the sources. I should comment on this source in that I threw a little bit of a surprise at you, in that I gave you what's known as a dependent current source. But these are really no big deal. All it just says is the current coming out of this source is just 5 times the current going through this resistor here. That's all it is, nothing too fancy, just if you can think of it as a little bit of amplification. And in fact, these sorts of sources are used to model things like transistors and the internal of operational amplifiers, which you may see next semester. Okay, anyway, so assigning our nodes, we have two trivial nodes here, and then we've got a ground node here. So those are three nodes. Then we have two other nodes right here, which are the ones that we need to solve for because they are not trivial nodes. So let's call this one V1 and this node V2. And if we solve for those, then we'll have everything we need to find our currents that we want to find. Okay, so now that we've got this, let's go ahead and assign current names. Now, again, with the exception of what's happening with this forcing current, we can assign currents in arbitrary directions as long as we're consistent and follow what the sources are telling us. So we've got a current that comes up through this voltage source from minus to plus. So that's going to go this direction. Let's call this I1. Then let's just go ahead and arbitrarily draw this current going down here. It likely is because it's going from a point of some potential down to a point of zero potential. So it seems like a good idea to draw it that way. Then notice what this current source is doing. It's going up into this node. So it's forcing us to go this direction, which we know this current is 5I3. Again, likely we're moving from a current going from a high potential down to a low potential. So let's go ahead and sign it in that direction. So this is I4. And then we're left with this current, which we'll just call it going this way. Again, as long as you're not violating the forcing direction of the currents versus supplies, you can assign these in arbitrary directions. The math will work out for you as long as you're consistent and not violating how these are forcing you one way or another. So again, that's typically how I like to do it, is to look at places going from high potential to lower potential. So we have a high potential to low potential here, high potential to low potential here, high potential to low potential here. We're being forced in this direction. And because we have a higher resistance over here, we're likely have a high to low potential here. So that's kind of my thought process. So the next step that we'll want to do is write our KCL equations. KCL here. Excellent. Okay, so let's start with V1. So remember that the currents entering a node equal the currents leaving a node. So we're going to have I1 is equal to I2 plus I3. And then at V2, we're going to have something similar in that we have I3 plus 5I3 from this current entering is equal to the current leaving, which is I4. So let's go ahead and simplify this a bit. So that's going to get us 6I3 is equal to I4. So already we've got now a description for I4, which is one of the currents that we are looking for. So we're getting on the right track. So the next thing that we need to do is go ahead and use Ohm's law, just like we did in mesh, to get this in terms of voltages. So again, here we have a voltage drop of across this resistor, so we're going to have I1 be 9 volts on this side, and then V1 volts on that side, so we're going to have 9 minus V1 divided by, in this case, R1. Now, a strategy that I like to use when solving these problems is to, because we're usually dividing by relatively large resistors, is to leave the resistances in their symbolic format for as long as humanly possible. And that, for me, makes things a bit easier to keep track of what's happening. Your mileage might vary, but that's my strategy here. So let's go ahead and set these, like bring this I2 over, and I'll show you why here in a second. It'll become clear why I do that, Again, it doesn't matter as long as you keep track of all your signs. You can do whatever manipulations that you want. So let's see here. We're going to do minus, let's bring I3 over. That's actually going to make things a little bit clearer. So bringing I3 over means that we have, again, V1 minus V2. Because we have a voltage drop, V1 is going to be higher than V2. So V1 minus V2 divided by R3. Okay. And then I'll just go ahead and set this equal to the easier one, which, again, this current I2 here is simply going from V1 to ground, so that's simply V1 minus 0, giving us V1 divided by R2. Okay, so that's our Ohm's law for that particular node. Now let's do it for node number 2. We've already gotten I3 here, so we're going to have 6 V1 minus V2 over R3. Again, just scaling by 6 here. And then that is going to be equal to R4, which again is just going from a high voltage down to 0. So that's just going to be V2 over R4. Okay, and here comes the most tricky part for node voltage method, in that the algebra can sometimes be a bit tricky. So usually when we're doing this, we need to be a bit careful. So what we notice here is we've got 2 equations, 2 unknowns. But the nice thing is that we have a relationship in a simpler equation between V1 and V2 that we can find over here. So let's tackle the simple one and try to relate V1 to V2. So let's multiply out. And bring R3 over. And then let's collect like terms. Okay, so then pull out this V2 here. Again, the goal here is to get everything in terms of V1 and V2, so I'm just trying to simplify this to make it as direct as humanly possible. So then, let's go ahead and solve for V2. We could solve for either one, but let's do it a little bit more complicated just to tease out some of the maybe more interesting points that we might not see if we do the simpler case. Again, it doesn't matter, you can choose which one you want to solve for. If you see an easy equation, if you solve for one versus the other, go definitely for the easier one. But in any case, we find that V2 is equal to 6V1 divided by R3 R4 plus 6. Now here we get a little bit lucky because R3 R3 is equal to 5K, R4 is equal to 1K, so we get this ratio ending up being 5, giving us that V2 is equal to 6V1 divided by 11. Okay, so now we have to bring this back over to this equation. Now that we've got a relationship binding V1 and V2, let's solve for the other. All right, so 9 minus V1 over R1 minus V1 minus 6V1 over 11 and all that is divided by R3 now, and that's going to be equal to V1 over R2. Okay, excellent. So let's see here how we want to solve this. There's a myriad of ways of solving this, but I'm going to multiply both sides here by 11 so that we can get that denominator out of here and let's see what that looks like. So we're going to have 9 minus V1 over R1, just forgot the 1 there. And if we do this, then we're going to end up getting minus 5 over 11 V1 over R3 is equal to V1 over R2. Okay, so now let's go ahead and plug in the resistor values. I mentioned bringing R3 over here. And sometimes this happens. Sometimes you think you see something that will simplify things and it doesn't quite work out. Still going to work out, but there really was no reason for me to bring that over there. But since we already started, let's go ahead and roll with it. It doesn't really change anything. So let's plug these values in. So you plug this in for 1,000, this in for 5,000, and this in for 2,000, and I've got a nice solver over here. If you end up solving for V1, you'll find that V1 is then equal to roughly 5.65 volts here. All right, so then we can then directly calculate I2 in this case, since we know V1. So I2 is equal to 5.65, which is V1, divided by 2,000. And then that will get us about 2.83 milliamps. So we found our first current. That's a good progress. So let's go ahead and find our second current here. So what we're going to do to find that second current is take our V1 value and plug it back in to here to solve for V2. So V2 is equal to 6V1 divided by, I'll do this again just for clarity, but again this equates then to 11. So we have V2 is equal to 6 times 5.65 divided by 11 equals 3.08 volts. All right, so then that means that I4 is then just V2 divided by R4, which gets us 3.08 volts divided by 1,000, meaning that we can look at this by inspection and say that this is 3.08 milliamps. And there we go. All right, and that just leaves us with problem 3. in which case we need to find the Thevenin equivalent and the Norton equivalent circuits. The nice thing here is that when you find one, you also find the other because they're related to each other. Oops, that should be an H. Via Ohm's law. So whenever you're tasked with finding the Thevenin or Norton equivalent, keep in mind that once you have one, you have the other. And we'll see that here. I think it's in the correction email, but typically when we don't have a load resistor listed, it's usually across the rightmost resistor. For your final, all load resistors will be appropriately labeled, so sorry about that. But let's go ahead and show that this is where the load normally would be, across this resistor here, with a load resistor attached here. So again, the first thing that we want to do is detach any load resistors. That is already done for us. And we'll also notice here that we've got a nice parallel branch that we can simplify. And if we simplify it, well then we're left with a circuit which we can either use mesh or node method to solve. Personally, I find node method a bit easier to solve circuits with, so that's what I'm going to use. But if you're more comfortable with mesh current, then by all means use mesh current. Oops. So let's go ahead and reduce these now. So taking these two in parallel will result in a resistor that is roughly 744.16 ohms. So let's redraw the circuit now. 5 volts. Typically with Thevenin and Norton equivalent circuits, it's helpful to redraw them as much as you can to help clarify things. I find that it reduces errors if you continue to redraw the circuit as you go on. So just a little tip. 744.16 and 2.5K. Okay, so again, I want to use node method to solve for this. This looks like a pretty good node for us to use. So I'll draw this here. Now the first thing that I like to find, again, you can find either the equivalent resistance first or the Thevenin equivalent voltage. Typically finding the Thevenin equivalent voltage is a little bit easier than getting the Norton current. So that's usually my strategy if you're not tasked with solving the Norton first, but typically if I'm given either option, the Thevenin equivalent's usually a little bit easier to do. So again, I'll go ahead and use node here. And what we want to do here is try to find the Thevenin equivalent voltage, which is the voltage across this open circuit, which is the voltage across this resistor here. So because I'm using node, let's go ahead and assign some currents. Again, because we're going from minus to plus here, this current will have a direction this way, probably going from a higher to lower voltage, so this current's likely going this way. And then let's just assign I3 to be this direction here, because there's likely a voltage drop from here to here. And then finally our current I4 heading down this direction, again because there's going to be a voltage drop from here to here. Okay, so let's assign our nodes. In this case, this node is what we're looking for, and then this node is what we need to get it. So let's assign that as V1. So with that, we'll then write our KCL equations. So I1 is equal to I2 plus I3. And then writing these out using Ohm's law will get us 5 minus V1, again because we're going from 5 volts over to V1, divided by 1.8K, is equal to, here's a voltage drop of V1 here, divided by the resistor value, 2.5K. Excellent. And then plus, what I'm going to do is combine these two resistors here. Because this is open, you can add these together in series and then use a voltage divider to calculate the Thevenin equivalent voltage that way. That's the strategy I'm going to use. You can assign a node and solve it that way as well. Both will work. So that's going to be V1 divided by 744.16 plus 2.5K. And all that is equal to 0 because in this class we obey the laws of thermodynamics. So let's go ahead and do that. Solving for this gets us a V1 value of 2.19795 volts, just to a ridiculous number of decimal places because why not? Then we'll notice that we can find this equivalent voltage via a voltage divider. So VTH, which is the open circuit voltage here, is going to be equal to the voltage input here, so V1 times the resistor value over which we want to find our voltage, so in this case R4, divided by this resistor plus this resistor. So again, R3 and R4. So R3 plus R4, which is then 2.1979, 95 times 2.5K divided by 744.16 times, or sorry, not times, plus 2.5K. And if we calculate that, we get a Thevenin equivalent voltage of 1.69 volts. All right, so the next thing we need to do is find our equivalent resistance. And to do this, we're going to redraw our circuit again, because what we're going to need to do is short circuit any of our voltage sources and open circuit our current sources. Since we don't have a current source, we just need to short circuit this. So the key thing to recognize as to what's happening here, let's go ahead and redraw the circuit. Here. Okay. Oops, there we go. Now we can see it. And I'm just going to choose this as a reference node just to demonstrate something. A very common mistake here is to assume that this resistor is in series here with this resistor. But it's not, because notice what's happening here. This end of this resistor is connected to this node, while this end of this resistor is connected to this node. Likewise, this end is connected to the ground node, while this end, because we short-circuited the voltage source, is also connected to this. So it's like this resistor has been shifted down to here. And by doing that, you can see that they are in parallel. So be careful here, because this resistor and this resistor are in parallel with each other. So I'm just going to black that out. That's still a wire, but just moving it down just to kind of see that this kind of, if you move it, looks like it is indeed parallel, and it still is in parallel here, but not series. So the goal is we want to get the equivalent resistance with respect to what's happening over here at the connected load. So let's work from this side over to that with reference to this open circuit where the load is. So this is still R1, this is R2. So we have R1 in parallel with R2. And so that's going to be 1 over 1.8k plus 1 over 2.5k, and that is equal to 1 over R1 parallel 2. So calculating for that then gets us an R1 R2 value equal to 1046.51. Okay, so let's redraw. So we found our parallel circuit here, so that resistor combines into a single resistor that we'll call R1 parallel R2. Now I'm going to point out a mistake that a lot of people make, myself included. The temptation is, again, to notice that to try and think that all of these are in series. But notice, because this is where our load resistor is connected, if we combine these in series, then that resistor is in parallel with this resistor. So let's call this R pi, and this resistor as R4. If we combine these two together, like they're in series, because we have this end connected to this end, which is then connected to another end, but when we combine them in series, that's going to leave us with a resistor that has one connection up here, one connection up here, which is the same as R4. So let's that's a little bit confusing, so let's just draw it out to prove that to ourselves. So these two are in series, meaning that let's just call this our parallel 2 is equal to R1 parallel R2 plus R pi, which then gets us a value of about 1.79, let's just call it 1.719 kilo ohms, or 1791 ohms. Okay, and so we now redraw this such that we have, I'm going to bring this resistor down, R pi 2 R4, and now we can clearly see that this end of this resistor is connected to this node, which is what R4 is connected to, and these two are connected to the same node as well, meaning that these two are in parallel with each other. So that means, finally, Req, or I should say 1 over Req, is equal to 1 over 1791 plus 1 over 2500, which then that gets us an Req value equal to 1043.3 ohms. And there we have it. We have our Thevenin equivalent circuit, which again is going to look like this. 1.69 in series with the Thevenin equivalent resistance of 1043.3 ohms. So now we need to find the Norton, which again we can just find via a source transformation. And source transformation is just a fancy term for noticing that these have a relationship between each other via Ohm's law. So we can simply calculate what current this would result in when running this voltage across this resistor. So again, to find the Norton current, all we have to do is use Ohm's law. VTH over REQ is equal to I Norton. So we have 1.69 divided by 10, 43.3 is going to get us 1.6 milliamps. And there we go. And we can then draw our Norton equivalent circuit, because remember, all it is just a current source with a resistor in parallel, and that resistor is REQ, between two terminals in which our loads are attached. And there we go. And that about sums it up for quiz number 2. If you have any questions, feel free to reach out. If you'd like more practice problems, be sure to check out my tutorial videos on nodal analysis, as well as Thevenin and Norton equivalent circuits. There's also a tutorial for phasor analysis, which might prove, will prove useful for the final exam. And with that, have a wonderful evening.